Right. Since it's almost 11:30. Yes. Okay. I suppose we should get going. So, CGVC 2017. Glad to see most people are here. A few people we're still expecting, but who knows. But anyway, our first talker, the invited speaker is Robert Lowry of Swansea University. He's going to talk about the age of data chaos.
Great. Thank you, Nick, for inviting me here. It's a great pleasure to speak in front of such an audience. And before I start, a little historical note. I did give a talk at Manchester Metropolitan University already, back in April. I looked it up, April 2007. And the title of the talk was, Are You Getting a Good Mixing? Was anybody here for that talk?
Same talk. Hasn't changed. How do you know? That wasn't it.
Martin, you might remember the next day I gave a talk at Manchester University, which you invited me. I don't know if you were at least at that one.
Yes.
Okay, so this is going to be a slightly non-traditional talk. So first I'm going to start out trying to convey this idea of the age of data chaos. That's a short introduction, and then we can look at we have 10 different possibilities we can look at in terms of this emerging from the data chaos. So the talk can go in 10 different directions. So there's going to be an element of chaos in the talk. And we won't be able to cover, happy Thursday, Dave. We won't be able to cover all 10 directions, maybe 2 or 3. And I'm hoping that the audience is going to choose which of those directions they're interested in hearing about. Right, so is this audience up for that exercise? Can this audience help with that? Yeah? Good. So we are collectively in this ubiquitous pattern of knowledge evolution, and it looks like this. Or it's also could be called the origin of the data chaos. So we're in the age of data chaos, right? And this is how we got there. And this is a pattern that everybody has experienced already in this room, right? This is a collective experience that all of the collective society is experiencing. Any society that uses computing is experiencing this pattern of knowledge evolution. It starts with a real-world challenge, right? We all have real-world challenges that we're trying to solve, like how to find this place, maybe. Maybe we're trying to build something like a car or a building. Maybe we're trying to solve a problem. Maybe we're trying to increase our understanding of some behavior or some phenomenon, right? These are all so the pattern of knowledge starts with a real world challenge that we're trying to solve or some goal we're trying to reach. And for every challenge, there's some sort of solution or approach in the physical world, right? If we're trying to build a car, for example, we could actually get out our hammer and nails and try to build a physical car. If we're trying to increase our understanding, we could maybe observe something, right, and follow it around to increase our understanding. But real or physical approaches or solutions to these real world challenges are often very, very difficult. right? Very expensive. For example, if we wanted to build a new type of vacuum cleaner, right? To really build a new type of vacuum cleaner would be very, very expensive, right? If we physically want to build it ourselves, right? Especially if we want to build, for example, 1,000 different prototypes, right? Happy Thursday. So real-world solutions or physical solutions to our real-world challenges and goals are sometimes impossible, sometimes they're not feasible, sometimes they're too expensive. So collectively, we are jumping from the real world or the physical world into the digital world, right? That's what this dashed line is. We all know about computers, we all know about software. We all assume that there's some digital solution to our problems, right? There's an app for that, right? It's a very common. There must be an app for that, or Google knows the answer to this, right? In the world of engineering, that would be, for example, computational fluid dynamics, right? And so, our real-world challenges, we search for solutions to our real-world challenges in the digital world, right? We think that there must be a software solution to help us solve these problems, right? Cars are built in software before they're built in hardware, right? Trains are built in software before they're built in hardware, and so on. All modes of transportation, all buildings, almost all physical objects are built in software now, right? Like the chairs and the tables, before they're built in the real world or the physical world. But looking for a digital solution to all of our real world challenges produces another problem, right? Another challenge, and that's what I mean by data chaos. So all we do now is collect data over and like forever because storage is so cheap, right? Sometimes we collect data with a special purpose in mind, like we have a hypothesis we want to confirm. Sometimes we're collecting data to try to run a business, right? Data is worth a lot of money. Sometimes we're collecting data just for no reason, just because we can, right? Does anybody here like collect things just for fun? Right? I used to collect things just for fun. And you do collect things, right? You're all collecting photos, right, on your phones. I have a huge collection of like 10 million selfies, right? So when we collect data, we run into another challenge and that's the challenge of data chaos, right? It starts already at the conceptual level, right? Like, what data do we have? Where is the data, right? What format is it in? Who has access to the data, right? Even right at the beginning, it already starts to get an element of chaos, right? Even before we start doing anything with it. And anybody that's worked in industry will certainly be familiar with their own company's data chaos challenges and problems. So we're here to promote the one solution to the data chaos problem, which is the visualization cosmos. Right? So visualization is a great way to address this challenge of data chaos. Right? If we want to increase our understanding of data and what data is describing and what knowledge it might hold, then visualization is a great way to go in terms of finding a solution to our data chaos problems. And I think most of the people in this audience would agree with that. Anybody disagree with that? Of course, that data visualization brings its own set of challenges with it. Right, so how do we create order from chaos? So visualization lets us explore data sets. Right? If we don't know what the data set is and we want to find out if there are any patterns or trends in there or outliers, visualization is very good for that. Right? Maybe we just want to find out what the data set is. right? This is a challenge for a lot of people. Visualization is good for analysis. This is the case when maybe you're an expert, maybe you collected the data yourself, and you collected it in order to answer a question, maybe confirm a hypothesis or refute a hypothesis. Visualization is good for presentation, so that's what we're going to use it for today. Right? After we've done our exploration of data and our analysis of data, we can communicate the results to a larger audience. It's also good for acceleration. Right? As soon as we can actually see the data, we can make decisions very quickly. Right? And we can see patterns within a few seconds, which might take days, or might even be possible if we were actually just manually reading numbers on a page or in an Excel spreadsheet. Visualization is also good for something increasing confidence. This is not so obvious for everybody, but as soon as you can see your data, you are more confident about the decisions you're making and what you're seeing is correct or incorrect, right? This is what happens at Swansea University all the time. As soon as we start visualizing data, we see errors, right? And we find errors, and then we fix them, right? And we increase our confidence by doing that, going through that process. Okay, so now we have some chaos. This is a little bit of a chaotic slide. And it has 10 different sort of case studies or demonstrations of going from data chaos to the visualization cosmos. And we can't look at all 10 of these, right? So I'm going to rely on the audience to choose one of these 10. If it wasn't so chaotic, they would be organized in a matrix of like 3 by 3. But it's 3, 3, and 4. It's just the way PowerPoint was sort of, happening at the time. So I'm just going to briefly describe them in sort of 1 or 2 sentences, and then I'm going to ask the audience which one they think is the most interesting one to start with. So we have a case study that looks at physics and foam simulation, the visualization of foam simulation data. Very, very unpopular topic, very specialized and very niche. We have a case study that looks at marine biology and animal motion, the study of animal behavior, especially for deep sea wildlife. We have an example of understanding call centers and caller behavior in call centers. So everybody loves call centers, right? It's so much fun to call centers. You can't avoid them. So we actually can visualize callers and their behavior. We have a case study on sports video visualization, which comes up with visual designs for rugby events and rugby games. Any rugby fans in here? Nice. We have an example looking at automatic streamline seating, right? So most streamline seating is done manually with a mouse and so on, but this is an algorithm that does it automatically. We have an example of streak surface construction. That's another flow visualization example. So a streak line is analogous to inserting dye into flow and watching the behavior of the dye. And a streak surface is like injecting a full sheet of dye into the flow and watching what happens to the sheet. We have another related example, automatic stream surface placement. So that's very closely related to the automatic streamline seating. It's another algorithm, but for stream surfaces, how to place them automatically in flow. In a tribute to the automobile industry, we have a case study of looking at chaotic flow through a cooling jacket. That's a good example of chaos right there. Everybody know what a cooling jacket is in your car? Anybody have their car overheat? Like that. That's what a cooling jacket is for. A broken cooling jacket will overheat your car.
Ever have your car under heat?
I don't have a case study for underheated cars.
It's almost as entertaining.
A frozen car. We have another example visualizing swirl and tumble motion. Actually, the diagrams are not showing up so well on this projector. But that's also looking at the process of combustion inside of an engine. And then we have a more generic example, something called texture-based flow visualization, which is using textures to visualize fluid flow. So now is the exciting part. I guess with a show of hands, I'm gonna go through these. And if you think you'd like to hear about one of these or choose one of these to start off with, you can raise your hand. You can raise your hand more than once, obviously, and whichever one gets the most votes, we'll start off with that one. And if we can't decide, hey, we're just gonna choose. That's a lot of power right there. Okay, any votes for the physics? 2, okay. I have to now try to remember the marine biology example. Okay, 6 it looks like. Call centers. 1, 2, 3, 4. Is your hand up there?
No. I realize it.
Testing me. Okay, sports visualization. 1, 2, 3, 4, 5, 6. So there are 2 for 6, I think now. The automatic streamline seating. Any flow with spans?
But I can make without it.
You might have seen. I think you've seen that one already.
I may have seen most of these already.
Yeah. Streak surfaces. 1, 2-ish. Automatic stream surface placement. I can tell you, we worked a long time on that one. That one took at least a year of of developing.
So what you're saying is Bob is voting for that. Okay, we understand this.
Cooling jacket. 1, 2, 3, 4, 5, 6. Oh, we got tie, a 3-way tie. That's great. That's great. The swirl and tumble motion, visualizing explosions in your car. 1. Okay, and then the texture-based flow vis. Okay, so we had a 3-way tie between the cooling jacket, the rugby, and the marine biology, I think. Should we do another vote just between those 3 to decide the 3-way tie? So
I'll do all 3 of them.
yeah, should we just do those 3 then? Okay, we can do that. So now I have to navigate the slides. That wasn't so chaotic. Maybe it will get more chaotic. So the first example involves a team of marine biologists. So there is a very lovely team of marine biologists at Swansea University. And they do an interesting job. They're trying to understand marine wildlife behavior. Now that's a special challenge, right? If you want to understand, for example, a cormorant or a whale or some deep sea diving animal, you can't just follow them around, right? You can't just get out your binoculars or something and then just follow them around for a few days. That's just not, so that's an example of some physical solution that is completely not feasible. It's literally impossible currently. Even if you could directly observe them, you might run into that sort of classic problem that your observation interferes with the experiment. It alters the results of the experiment itself. So they turn to a digital solution, as most people do these days. They have little sensors that are getting smaller and smaller every day, and they actually go out into the wild. They catch the animal and they stick the digital sensor on there, release the animal. The animal does its thing, so to speak, for a few hours or a few days. They recapture the animal, grab the sensor, bring it back into the laboratory, and try to figure out what happens to the animal during that time. Very, very challenging task. And that sensor records things like acceleration, right? Accelerometers are everywhere nowadays. Temperature, the local temperature, the local pressure, the local ultraviolet light, and as a number of other environmental variables at anywhere from 10 hertz to 30 hertz typically, right? So it's a lot of data. So what do the marine biologists typically do? They typically go into the lab, download the data, and then they plot it like this as time series plots, right? On the x-axis is time, and on the y-axis is amplitude. And they claim they can infer animal behavior by looking at those time series plots. I actually don't believe them. I think they're lying. They're just publishing false results. But for example, they claim they can associate a diving pattern with some of the wave patterns in acceleration. This is actually the x, y, and z components of acceleration on 3 separate axes. So that's already very challenging right there. But they claim they can infer different kinds of behavior by looking at those plots, and it takes a long time, right? That's a search process. It's mostly a manual search process, although we have developed methods to try to accelerate that using machine learning. But they asked us, can you help us do something better? Can you help us visualize this data in a better way that increases our understanding of marine wildlife behavior? So we said no. No, we said, yeah, sure, of course we can do that. And this is what it looks like. So the first thing we did, so that's the cormorant about to die. The first thing we did was we reconstructed the accelerometer data into a vector, right? Instead of 3 decoupled components, we have now a vector, right? And we attach it to the center of this polar coordinate system, right? And now we can see the orientation of the animal in a very intuitive representation. Right, so that's the first thing we do. We have the original view of the data, which is what the biologists are used to. The user can select a special time range, and it gets plotted in both the spherical coordinates and the traditional time series coordinates, right? So the accelerometer is normalized and then positioned at the center of the sphere, right? And if we now track the accelerometer vectors, we can look at the orientation of the animal over time, right? And if we then plot pressure to radius, so increasing pressure means it is an increasing radius, we can identify easily descent behavior inside the measurements, right? The pressure stops, and now the animal begins to swim in the deep sea, right? And that shows up very, very clearly in this kind of visual representation rather than a traditional time series. We also tried some large data visualization experiments. So this is a spherical histogram of the data, right? So these large bars are the most frequent animal orientations, so the most frequent animal postures. So we know that the animal spent the most time in this posture or this orientation compared to the others, right? That's what we can learn from the spherical histograms.
Question
Yep.
for you. How did you parameterize the sphere on that one?
That's a very good question. I prefer not to answer.
Too bad.
That's a very good question. So I'll have to pause it to try to answer that. So I can say the answer is non-optimally. So we did not optimize the tiling of the sphere or the perimeter. So it's the most naive parameterization or tiling possible. It's just drawing lines from one pole to the other, just like in the globe, the
You mean latitude,
latitude, longitude lines on
Right.
the globe.
Does that induce a distortion in your presentation of the result?
Yes, it does. It makes it makes the presentation not perfect. That's true. And it turns out that is a fun challenge. So that's why we didn't work on one bite at a time, so to speak. That was not the focus of the optimal parameterization of the sphere. Was not the focus, but it would be a great future project.
Mm-hmm.
So we can also apply clustering techniques to the data, right, and assign those data samples to different clusters, right, and those different clusters are associated with different postures, the animal postures, right. So we can do a fuzzy clustering, or we can do a discrete clustering, and we can do a probabilistic clustering. So this is the user changing the probability of any data sample belonging to one of the 5 clusters. Right, and we can also make discrete representations of those clusters. And then we can represent the transitions between states or postures in the graph, right? So an edge from one to the other is a frequent transition between one posture to another, right? And the thicker the edge is, the more frequent that transition is from one posture to another. So it's really like a finite state machine representation of animal behavior. Any other questions on that one? The more challenging the question is, the better.
How did you decide on the number of clusters?
That's a good one too. That is going to be driven a little bit by the domain experts. The domain experts are going to have hypotheses about the number of postural states that the other answer is trial and error. The third answer are heuristics.
Yeah.
But that is an unsolved problem, right? If anybody has a solution, I'm open.
Could you base it on the expected behaviors?
Yes, so that's the way the marine biologists come in. Yes, yes.
Okay.
Yeah.
So what do you do? Do you take their estimate of how many different behavior patterns there are and double it, just in case, or do you take it exactly?
It's trial and error, so we try a few different things. We take their estimate exactly, we
Mhm.
double it, we explore that cluster of parameter space.
Right, so what do you learn by that exploration?
That 5 is a good,
Yeah, but equally, if that 5 is the number that the marine biologists estimated, then if that ends up giving best visualizations, then that's a good confirmation of our hypothesis. If they, however, estimated 8 and there are only 5 clusters visible, then there's insight to be derived from that too.
yes, definitely. This what I presented is really just the beginning, right? This was really the first steps. There's lots of possibilities, future possibilities for this. Yeah. So the gentleman in the corner has, couldn't get a chair. I have a chair here.
Get a chair. There are plenty.
I also have some questions about the clustering, because what I did was like non-parametric Bayesian clustering myself.
Okay.
So
Okay.
that naturally comes to, well, can you go in more details about the trial and error processes? And how do you validate your model, for example?
So the trial and error process is picking a number, trying it out, and seeing what it looks like, right? And for the validation, that's up to the marine biologist. So this is something really that we don't know what animal behaviors to look for. We don't know what to expect exactly. So we rely on the marine biologists for their input and what they think is correct and what seems to be incorrect. And they also have results, right? So we can compare our results with their results for validation, right? And see if there's any correspondence. I see the interest on this one is very high. You know, I've been in front of audiences and nobody chose that one at all. I think, I don't know, anyway, earlier this year. Okay, the next one, which was was it the sports one?
Yeah.
Oops.
Call centers, I think.
Let me see if I can remember. So we had the marine, the sports, and the cooling jacket, I think, were the winners, right?
Sports.
Sports or the call center?
Yeah.
Sports.
No, sports and the cooling jacket, I think.
Sports and the cooling jacket.
Okay, yes.
We could do another vote.
No. We'll see how much time you've got left.
We'll
Come
include,
on, last 2 years voting has produced better results.
a referendum, we could, oh, I won't use that word. Oh, I already feel like.
We can also have the judge's opinions.
Okay, so the sports visualization.
Sounds like extreme sources have been voted off the island.
This one is completely different, which makes it fun too. So everybody here watches rugby, right? I've actually, I'll give away you a little secret. I have never seen a rugby game in the traditional sense, like by sitting and watching it from start to finish. I've watched rugby games in this sense, but never the traditional way. But it's still on my to-do list to do that. It's embarrassing, actually. So this is rugby is a field sport, right? For anybody that's not familiar, right? And there are two teams, and they try to score goals or tries in the rugby knowledge. They try to bring the ball across the field, you know, the offense, and then there's a defense. And what's the goal? The goal is to win more games, right? That's the goal in this case. That's the real world challenge. Now, what's the analog or the physical solution to winning more games, right? Earning more money, hiring the best paid people. Hiring more people, right, is one of the ways to do it. And study the video recordings of the games that teams play to try to understand their strategies. This is the traditional solution to winning more games. But it's not very difficult to imagine how challenging those solutions are. Right? If you're trying to understand a team and how to beat a team, theoretically you'd want to watch their previous games, maybe their previous 10 games. I don't know how many games they try to study. But to watch a rugby game is very costly, right? It takes a long time. I guess it takes 90 minutes or something like that. So if you want to watch the previous 10 games of a team's game, that's very challenging. And to do that for every match, like every time you face an opponent, very challenging. It would be interesting to know a little more about how much they try to do that in the real world, how much of these videos they're really watching. But that's only one of the challenges. Imagine you're watching your 5th game and you see a special kind of goal scoring event, like a special try, and then you're taking your notes and you think, oh, did I see that? Didn't I see that same player do that same trick like 2 games ago? I think I saw that. And then imagine having to search through the videos to try to find, like to correlate events, finding patterns, finding outliers, finding the strategies. Very, very challenging, really, really challenging. So the question is, can we come up with a digital solution that's better, right? And can we use visualization to try to sort out that really challenging, chaotic task? Rugby, so for Americans, like, rugby games look very chaotic. They really. So that's what we worked on for a while, to try to come up with a visualization solution that helps trainers and players and practitioners and so on come up with ways to study rugby games and the events inside of rugby games to find patterns and different strategies to win more. And one of the components of the visualization is a rugby glyph, a high-dimensional rugby glyph. This is what a rugby glyph looks like. It's very, very beautiful. And there are something like 10 different parts to the glyph encoding different information or different events. So each event inside of a rugby game is mapped to a glyph. So that's a feature extraction process right there. But that's already happening. So at the professional rugby games, there are people, professionals, sitting on the sidelines, and they're recording all the events using special hardware and software. They're already doing that, right? It's our job then to take that and visualize it or somehow come up with a visual design. This is one of them. So inside is a so-called pictogram that represents the type of event it is, whether it's a scrum, or turnover, or a try. It's the start event for every start of a play. Time and event duration are encoded here, so we assume that the start time of the game is at midnight, and this is the time, and then the duration is encoded by the thickness of this glyph component. Tortuosity is something we derived, so tortuosity is a ratio of a straight line. So in the ideal world, a player would run in a straight line towards the opponent's goal, but that's not what really happens. It's the ratio of that straight line to the actual path, which is full of curvature, right? So the more curved the path the player took, the higher the tortuosity, and that's encoded in this curved area here. Territory start position is mapped to radius, so the radius up here. Contour color is mapped as a team identifier. Right, so each team gets its own color on the contour. Net lateral movement is encoded in the arrow width. So the width of this arrow, so if this is the longitudinal motion, the latitudinal motion is orthogonal to that, and the amount is measured to the width of this arrow. The number of phases that each event is associated with is encoded just as a number inside the arrow. And the direction of the ball play is encoded also in this arrow. So the direction of the ball play in this case is in this direction. And then we have the pictogram depicting the type of event. And then the gain, so the distance towards the offensive goal is encoded in this color, this inner color here. So that's a glyph. It represents one event, and then what do we do with those glyphs? We plot them on a scatter plot for a whole game. So this is what that looks like.
Glyph sorting
I can
in
turn
terms of
off the
visualization.
So we can actually plot all the events on a scatter plot and then get a picture of a complete rugby game immediately, right? So time is on the x-axis, in this case the gain is on the y-axis, and we can see, for example, this is halftime, right? All the events in the first half, all the events in the second half. And the events that are associated with tries are highlighted with this purple halo. Right, so we can immediately see what kinds of events are associated with tries. Now the axes can be changed, the axes of the scatter plot. Right now the user has chosen event type as the x-axis along the scatter plot, and we can see right away that all the tries are associated with lineouts immediately, right? Just a few seconds. So that's a special kind of event. This is territory start position versus time, right? And another thing that's happening here is we have multiple coordinated views. So this is the glyph, this is a generic glyph, and the user can click on different parts of the glyph and then sort the actual plot based on what the components that the user has chosen. So that's an interactive glyph interface, right, that can be used to decide what the focus should be at any time in the scatter plot. Right? The user can select subsets of events that they're really interested in learning more about to get more information, right? And explore the different properties of the game. We also have a hierarchical sorting strategy, so we know it's all the glyphs overlapping. So we can scale the x-axis, right, so that the glyphs don't overlap as much. And then we can do another sorting on that subset, right? Notice the big clump of try events, right, associated with lineouts. So we know that the lineout is a very successful event in terms of scoring points, and we can identify that immediately, right, rather than just watching a game for 90 minutes and then taking notes about which events are associated with tries. Right, so that's the user using a hierarchical axis binning to try to alleviate the overplotting and inclusion. Here we're sorting by a different metric, right? On the y-axis, the start time, right? The start time versus event. And then we can use this to also compare different matches with one another, right? So we can compare gain versus tortuosity, for example. We can ask ourselves, is high gain associated with high tortuosity or something like that? And the answer is no, not really. We see in the scatter plot for that game. We can load in a different game, so that's a different game. In the plot, the plotting parameters are exactly the same, right? So we load in a different game, and we can compare the two plots with each other, right? That's loading in a different game, right? The first game again. And then we can try different sorting strategies to try to compare the games. Again, we see lineouts as being associated with lots of tries in this case, and turnovers are also associated with tries. We have a user option that just lets the user see the average values for any of the groups. And then again, we can look back at the second game and make a comparison, right, and make observations based on those comparisons. Right here, the tries are associated with all the different events in this game. So whichever team scored those has a better strategy in terms of being able to score points using any different kind of tactic. Any questions on the rugby one?
3 questions.
What's your name, by the way, and affiliation?
Nhl Wang from Leeds.
Oh, okay,
I'm
good.
talking with Hamish.
Okay, sorry about that.
Well, now you've been introduced.
I'm sorry to put out.
Yeah.
Sorry. 3 questions. You probably have explained that, but I missed that. So first, how do you automatically detect those events?
Yes.
Or what kind of thing are defined as events? Okay.
Yes.
Second one is, what do those lines mean? Do they mean semantically dependencies or temporal dependencies? So that. The third one is, if so, I wonder, since you already can do visual comparison, then you already know the results of the matching of the games, right? Could you potentially learn a ranker, for example, to tell you the optimal strategy for next game?
Have you seen this before?
No.
How did you?
I'm
I
thinking
can't
about the
believe
AlphaGo
you.
actually.
That-
I'm thinking about the AlphaGo, the whole structure, which actually the similar features of your graph can be used as input, and an output will give you ideally optimized strategy for next game.
Yes, very good questions. Very good questions. The first question was about how do you define events
Or detect.
or detect events. I am happy to say that I don't have to worry about that and decide that.
Okay.
It's the experts that are recording the data on the
Labeling.
sidelines that are being paid to do that automatically.
Could you replace them?
Oh, that's a vision problem. That's not I would say that's a computer vision challenge.
Okay, so for the sake of this one, it was your data provided, fair enough.
Correct, yes. So there are people already paid on the sidelines recording the data and deciding what an event is and what's not an event and so on. So we don't have to worry about that. Those are rugby experts, by the way, those people recording that data. I wouldn't be a good choice to decide that. But we could continue on that discussion because to define an event is a non-trivial task, and that's why you ask that. So I know that there's a significant body of literature on just that topic. And as far as I know, there is no consensus on a precise definition of an event. And the only agreement that I've seen is that events exist, but their exact definition is still up to debate. The second question, refresh my memory.
Lines between events.
Oh yes, I didn't mention that. That just means that they're successive events. So if there's an edge between two, it means they happen one after the other. And then the third question, the advanced question is, can you come up with an automatic? Well, what we worked on as a follow-up for this was an automatic ranking of events in terms of their importance. And we used a machine learning algorithm so that the user, an expert, would take a subset of the events, rank them in terms of their importance, and then apply a machine learning algorithm to the rest of the events to rank them automatically. So those are three very good questions. I think you've used up your very good questions for the day. I can see that Hamish is
Not going to ask a question.
his like transferred some serious stuff over there in Leeds. Dave?
Was it?
You mean I've infected him?
Was it just used for post-match analysis, or is it used in real time in the game? And if it's used for real time in the game, suppose both teams are using your software. How does that change the nature of the game?
Ooh, I have not got that question yet.
Well, there's always a first time.
So the first question is, this is post-processing, so to speak, so post-game. However, there is another project, the Matchpad project, which was implemented on tablet devices and iPads and things like that, that can be used during matches, actually. And there's even a spin-off company. I don't know if it still exists, but at one point a spin-off company existed just for that very purpose. Now, I don't think we ever found out what would happen to a game, how that would influence a game exactly. I think it would take a long time for the coaches and trainers to build up the trust necessary to say, okay, I'm actually going to change my decisions based on this amazing software.
They don't have the ability to contact them.
That would also be a legal question,
Yeah.
I think. There would be like the game legality questions involved in that. What technology are you allowed to use to influence your game? And you can't just use anything, right?
You meant much more American question. If you did it in ice hockey, there's a tactic of ice hockey. But in ice hockey, there's a tactic of basically being a person who's being a disruptor, who will go after a certain other individual who is performing too well. Now, he may not, normally these people are very good at knowing who that person is, but this system would actually work that one out quite quickly.
Yes.
And if it highlights somebody who's just is doing really well but nobody's noticing,
Yes.
this thing will find out, and then that's the person you disrupt.
Yes.
So do go on the question.
That's what I don't like about ice hockey. I don't even
Yeah,
think
no,
we
I
should.
don't.
I would just
Try not
not
to use
even
the word
have
fight.
ice hockey as a professional sport.
Right, you've got that one. But I think that's how you can see things. The question is, how do you evaluate something like this? In the sense that, how do you get feedback to say, are your glyphs or are your structures? To us, it all looks really cool. And
Yes.
actually, if that was streamed live whilst we're watching the game on TV, this could be quite an interesting extra thing for a TV broadcaster to do as a sales page.
Yes.
But the question
yes.
is that different from it's definitely a different evaluation from an expert saying, I've actually gained some insight from this, and thank you, and
Yes.
here's what I've done. Whereas you may say, yeah, we always knew that Dynaps were scoring all the tries because it's fairly obvious. And I
Yeah.
always wanted to
Yep.
watch the game, so it's not really helping me. But then I think he can get more statistics if something unusual came up. So it's how
Yes.
do you go to
Yes.
that next stage of basically working out which bits of the glyph you should emphasise on and which bits you can drop?
So we worked with a sports scientist at Swansea University on this project for guidance on what he thinks is important. And we also worked with the Welsh Rugby Union to get some feedback on what they think is important. But what is important is going to be a function of the user ultimately. So for different users, they're all going to have their own opinions about what they think is the most important thing. And that was partially the inspiration for the next project, which was the ranking. So every person is going to rank the importance of events differently. And that's why we have this project that lets a user choose their own ranking, take a subset of events, rank them according to what they think is important, and then apply it. But that's the idea, is to get the feedback. That's one of the things that these projects all have in common. They're really done, with a domain expert or multiple domain experts to get their valuable knowledge. Does that sort of answer your question? Yeah. Any other rugby? The enthusiasm is really high in this audience. Really high.
In defence of ice hockey, all I will say is that if Martin continues with that line of assertion, a disruptor may emerge from the audience.
Do you guys remember when there was the Nhl Strike? There were 2 years when the NHL didn't perform at all. I thought it was great. I thought it was great. Like, okay, I didn't miss it.
Well, are you sure you want a disruptor to emerge from the audience?
I actually had a theory that would be the perfect time for football or soccer to inject itself into the North American sports collection, so to speak, to replace the ice hockey.
You can't play football when it's 20 degrees below zero.
Maybe indoor or something. I don't know. But anyway,
People do, but
in
one of the
Canada,
major driving factors is simply the weather.
yeah.
That it is a more practical game in the intense winter. Let us leave aside personal opinions as to whether it's a brawl or a sport. Right? If you're going to analyse something, you should step back from your subjective opinions.
Yes. Okay, so the third case study, the cooling jacket, less controversial, the least controversial case study. I love Canada, by the way. I love Canada. So,
especially with a bit of maple syrup.
we all know and love cooling jackets. This is the most chaotic data set, I would say. Well, it's definitely has a high level of chaos, let's just say that. So the cooling jacket is part of your engine, right? And the job is to transfer the heat away from the engine so it does not overheat, right? So it's a heat transfer case, right? And the analog solution to designing a cooling jacket is to build real prototypes, right? That's the analog solution. But that's very, very expensive, right, to build a physical cooling jacket. So engineers use computational fluid dynamics, right, as their digital solution to simulating the flow through a cooling jacket. And this is what the cooling jacket looks like. It has three main components. It has the cylinder block, or the lower half, right? The fluid is injected. This is the inlet. The fluid is injected in this part. Then there's the cylinder head. These are 4 cylinders, by the way. 1, 2, 3, 4. So the 4 cylinder block. The cylinder head, right? Well, again, 4. And this is an outlet where the flow comes out. Now, the difficult and chaotic part is the gasket in between the cylinder block and the cylinder head. So I've taken these 3 components and exploded them, so to speak, and then depicted the gasket. Now, the gasket is what connects the block to the head, and it's a series of holes, small holes, right? And this is where the greatest degree of freedom is for the engineers. The engineers can place those holes anywhere along the surface of the block, between the block and the head, right? They don't have so much flexibility in terms of the geometry of the block and the head, but they have a lot of flexibility in terms of where they can place the holes, how many they can use, and their size and orientation. Right, so this is just one configuration. That's what these red things are. They're the holes where the flow comes through, right, from the block to the head. And the goal is to have a longitudinal flow component from the inlet to the outlet, and a transversal component, which is from the block to the head. So the ideal cooling jacket has those 2 and nothing else, right? Those 2 flow components. Because we want the flow to come in the inlet, run smoothly somewhere, up and out, right? To transfer heat away from the... And we worked on a project to visualize that flow. And what they really want to see the most of, so to speak, or the focus, is where the flow is misbehaving. So if you get an area where you're injecting flow and then the flow is just circulating, like as a vortex, and just not moving, then it's going to overheat. It's going to cause bubbles, right? And could cause other things other than just overheating. High pressure, for example. So let's look at that demo. I'm glad you guys chose this one, because I haven't shown, this one is something that we haven't seen in a while, and if I can remember which one it is, that would be good. So this is what visualization of flow through a cooling jacket looks like. Oh, this is the, okay, yes, this is the right one. So if we apply texture-based flow visualization, so that is some very, very complex flow, really complicated, right? And it's also a multi-scale flow, so we have patterns of flow at different scales. Some are much larger. This is a zoomed-in view of the flow just at one of the cylinder heads, right? So we tried lots of different kinds of flow visualization techniques. These are stream surfaces that are seated at near the inlet, and you can see the flow going up from the cylinder to the block. Then you can see some flow that gets deflected and then just runs into a vortex. Right, this is the stream surface color mapped to velocity, or just one stream surface color mapped to velocity. It's very complicated, as you can see. Right, and it slows down. You can also see that the flow slows down between the inlet and the outlet. This is using particles to visualize the flow behavior, so releasing a set of dense particles at the inlet and watching what happens to them as they traverse the cylinder geometry. These are pretty well behaved paths, so you can see both the transverse and longitudinal flow motion from these particles. You can see those that some of them get sort of stuck for a little while before the gasket, before they finally escape. And this is extracting the flow topology, so those are critical points, right? There are lots and lots of vortices inside this complex geometry, right? And vortices are actually undesirable flow behavior in this context. So there's a lot of imperfect flow in your cooling jacket, or at least in this cooling jacket, which is one of the reasons why cars overheat so hot. Right, these tubes represent vortex core lines, so those are centers of swirling motion. So this is these are also a different method being used to extract vortex core lines, so those are the lines of swirling motion, so they're axes of swirling motion. And this is using like the scatter plot of pressure versus position. So one of the goals is to decrease the pressure gradient between the inlet and the outlet, and we can see areas of very high pressure or high pressure gradient using some information visualization techniques. Right? High pressure gradient is something they're trying to avoid in the cooling jacket geometry.
Is that scatter plot from particles, or where are the observations derived from?
Those can be, for example, on a cell by cell basis. So the geometry is composed of mesh cells, so you can plot data based on cells. That's one of the possibilities.
Okay, so I'm going to ask two related questions, which I'm afraid are fairly obvious coming from me.
Okay.
Number one, did you consider using the continuous scatter plot technique?
No, we didn't consider that. That would be a great piece of future work. Great.
Number two, would you like to try the fiber surfaces with it? Because, in fact, that's one of the things that's targeted at, is the relationship between pairs of variables in a continuous domain.
Yeah, I would be happy to try it. Happy if I understood them.
Well, in case, I will thug you over this evening so you do.
We need a fiber surfaces tutorial. This is to help with that.
I'll invite me down, we can probably arrange it.
Any other questions on the cooling jacket? One of the other things that we wanted was to release the cooling jacket into the visualization domain, and we did have it available. If anybody's ever interested to use it other than English, please let us know. But it's very challenging, right? I think a lot of people are afraid of that data set. Essentially, it's really challenging.
So we're doing currently this simulated project going on with a big company around the corner. And they are doing hair products and making mixers. And at the moment they're doing the rapid manufacturing to make the mixers and then the real simulation, as well as the simulation using OpenFOAM to try to reduce vortices in similar area. The issue comes is, what are people actually imaging the real modalities in? Because in the chemistry and the pharmaceutical side, they're using just 1D tomography or 2D tomography, very poor quality, and they're trying to relate that to the high resolution simulation which you get.
Yes.
Is that a similar problem?
Yes, it is. So it's hard to imagine, but this was done in conjunction with AVL. So AVL actually has translucent and engine components. Glass engine components, so they can make observations directly with high resolution cameras and so on. I cannot say I was ever involved with that though. I never got involved. But they do attempt to make special components where they can make direct observations of this behavior. But I don't know the details. Yeah. And I imagine that equipment is really expensive.
And they have different characteristics which basically don't do the same mixing.
Yes, and I also know that the simulation communities, the flow simulation community and the experimental flow community, they're separate essentially. And the experimental flow community pokes fun of the simulation community and says, oh, you guys are doing those fancy simulations, but we don't think they're accurate, right? And they just, and there's some rivalry, let's say, between those two communities, yeah. So which probably doesn't help very much, right? Another question?
So we're given the simulation data, or actually using some simulator to simulate.
In this case, we're given the simulation data. Yes, yes. So that's another interesting aspect about this. This is a real problem, so to speak. It's real data, real cooling jacket geometry, which is unusual. I've never seen it anywhere else, actually. I thought maybe there would be a few follow-up papers that said, hey, can we use that cooling jacket? Never did I see it outside of this project. Any other questions? How are we doing for time, Nick?
You've got lots of time.
I think there's going to be a supplemental vote.
Yep.
Is it possible to change the gasket?
Yes,
Okay.
exactly. That is what they changed. That is the parameter, but it's like a very complicated parameter space, and I think I never heard of any really systematic methodology by which they modify that parameter space. And I have a feeling there's a lot of trial and error going on there, a lot.
Did they actually modify it based on the visualizations or based on something else?
No, the answer is no, they didn't. We didn't succeed in that part of the feedback loop due to some time and logistical constraints. Yeah, but that's the ideal case. They see the visualization and they modify the gaskets.
It's often the hardest part of the loop.
Yes, yes. I'm glad you guys chose the cooling. This is the first audience to choose the cooling jackets, the cooling jacket example. Okay, I'm going to leave the decision up to Nick.
Oh gosh,
about
decision again.
So
Yeah.
we could go to lunch. We could have a break, or we could
lunch-
choose another.
Lunch has to arrive in the other room.
Is that what that thumping sound was?
Not for another half hour.
What was it, a rugby game?
We could. Why don't you do a vote to talk about call centers?
Well, we can do a vote. Well, shall we do a vote? Add to the chaos? So you're not allowed to vote for the ones we are.
We're going to have another argument.
So we have the physics and the foam simulation, one. The call center behavior. Yeah, that's 1, 2, 3, 6, it looks like. 7. Automatic streamline seating. I quite like that one. Streak surface construction, they're all good. They're all really good, by the way. I forgot to mention that. Stream surface placement, swirl and tumble motion. This is another automobile engine one. And the texture-based flow is okay. The call center looks like the winner in this case. I like the how different this one is compared to all the other ones. This one's really an outlier in my opinion. So we are working, this is a work in progress, by the way, this one. We are working with a company called QPC, and QPC is our experts at collecting chaotic data. Experts. They're partially the inspiration behind this talk, actually. They don't know it though. So what does QPC do? QPC, they have a hypothesis that says if we record every event at the call center that takes place, we can make recommendations to the call centers on how to improve their operations. That's their hypothesis. So they have written software that collects everything, every event that happens in a call center, right? Like the number that called the call center, when they called, which buttons they choose in the IVR, the interactive voice response system, right, the menu that you get when you call a call center, how long you are put on hold for, which agent you talk to, how long you talk to that agent, if that agent put you on hold or transferred you to another agent or put you on hold and made another phone call while you were on hold, all sorts of different events, so every event in a call center. And when I first met QPC, I thought that's that's a funny niche problem. But actually, it's not funny. It's not niche either. It is kind of funny in some ways. It's not niche. So, for two reasons. One is we all have to call call centers. Has anybody not called a call center? Like, you don't have to, literally have to, but chances are you have spent some part of your life like interacting with a call center. But the other astonishing thing is how many employees call centers have. So in the UK or in Europe, the number of employees in call centers is equivalent to the population of Wales, like all of Wales. It's around 4 million. Like really a serious number of people are employed in call centers. And in the UK, it's a very, very high number. It's like 3% of all employed people work in a call center. It's something really, really big. I don't know the numbers off the top of my head. You can see the paper that this is based on for more numbers. But it's huge. It's huge. And so if we can make any small improvements, or we can help study this problem and make recommendations in any way, it could have a really big impact. So understanding call center behavior is the goal, right? If we were to think about an analog solution, we could theoretically hire more people, and we could theoretically hire people to make observations, like watch what happens in the call center, take notes, and try to make recommendations based on observations. That's very, very difficult, right? It's very, very costly. So QPC decided, oh, surely there's a digital solution to this problem. We're just going to create a database that stores all the events, right? And they run into the same problem that everybody runs into, right? They collect and collect and collect, and they realize, oh, to actually extract useful information and knowledge from this collection, this huge collection of events is really, really difficult. So it's millions of events. In this particular case, it's over 200,000 phone calls in a single day, and each phone call can have anywhere from 1 to 200 events, right? So it's millions of events, actually. So in our first stab at this is a tree map. We're going to show the demo, but before I show the demo, which moves really fast, we'll look at a preview. This is a tree map view of all the events in the call center. The largest rectangle of the hierarchy represents 1 day of calls. And each square represents 1 hour of calls. And then the rectangles inside the squares represent the volume of calls in that hour. Now that's only, by the way, the start time of the calls. So they're organized by start time as opposed to duration. Right? Some calls, believe it or not, last several hours. So there's no connection, there's no call that like covers several hours, but it will show up as a large rectangle at the bottom level of this hierarchy. Right, so this is when the call center is closed, right? So the call center gets lots of calls when it's closed, right? And then here's the first hour that it's actually open. And you can see just from the tree map that where the largest volume is, right at lunchtime. So everybody likes to wait at lunchtime. And then color is, in this image is mapped to the percentage of abandoned calls. So this is what call centers want to minimize, is the number of abandoned or frustrated callers that don't achieve a resolution to their problem. And you can see just from the overview already, the percentage of abandoned calls generally increases with every hour, right? Because it's mapped to this red color. So every hour, generally speaking. So that I like this image because this was the first time anybody, QPC or us, had ever seen an overview of the calls in a day. It was just the first time. And then there are different user options to filter those calls, and we can drill down to different levels in the hierarchy. So let's run the demo. So this Richard Roberts actually has his voice on this demo right now, so he's speaking. These are different images that the software can produce, by the way, the tree map software. So we can use the tree map to get an overview of all the calls in one single day. So that's it. This is also a histogram that shows the volume of calls by hour, right? And then the color is usually not, the color map can change, but it's usually based on the percentage of abandoned calls. I mentioned one other thing because this video goes very quickly. The hours are divided up again into 10-minute blocks. So these are 10-minute blocks, and there are 6 of them. And then each 10-minute block is divided up into single block units. And again, the size represents the volume of calls inside each of those minutes, inside of each 10 minutes. And we can, as we'll see, we can zoom down to the individual calls.
So if there's 10-minute blocks, what's the lower 6?
And then the block is quite big.
Yeah.
So it's
Every minute.
It's 1 hour, right?
Sorry. So you've got it's the main division.
That's
then
right.
it's
That's right.
divided
So
into-
here's 1. Yeah. And
Okay,
then there's
sorry.
the second one. Here's the third.
Sorry.
4.
Yeah, I understand that.
Yeah.
Sorry, it just looks as if you were pointing only at the top.
Refresh my memory what the 24 boxes.
24 hours in the day.
Okay,
1
so
box per hour.
1 box per hour.
Yep. It's a temporal hierarchy.
So each of the small blocks is 1 minute. The tiny
Yes.
blocks.
Yes.
Got it.
That's right. Day, hour, 10 minutes, 1 minute. And then individual calls, which we can't see in this particular view, but we can zoom in.
And sorry, and if something carries on from 1 hour to the second one, it's included in the second one.
It's based on start time,
Yeah.
so what we see is the start time. And
Yeah.
it will show up, a long call will show up as a large block at the lower level, but it doesn't reach into the other time. Into the other time. So length is mapped to the size of the lowest rectangle, but it doesn't stretch into the other
So
boxes.
it's actually slightly more busy than it looks.
Another question? I'll pause it. Yep.
Yeah, just so that the squares near the end of the day become redder and redder. Is it
Yes,
just because there are just too little time for them to find resolutions, or any other?
that's the question. That's
Okay.
a very good question. Who invited you?
I volunteered.
Hamish invited you.
Well, I believe I sent out a public announcement.
Yes, that is the big question. Why do people want to abandon their calls as the day drags on? My guess would be people have less patience the more the day drags on. But there are other hypotheses we can.
Could it be just that there's not enough staff?
Yes, there is psychic power happening in this room.
No, we already saw the next slide.
Oh. Yeah, so the staff is also changing, right? And the number of staff could be affecting the number of abandoned calls. Right, so now these are filtering options. Unfortunately, they're not showing up so great on this display. But we can change, for example, what we map color to, the percentage of abandoned calls, or the length of time that they spend in the IVR, or the length of time that they're put on hold, the length of time that they're talking to an agent, right? And we can also apply focus and context filtering techniques that we'll see.
So, what's the thing down the histogram down the right-hand, left-hand side?
This is a histogram of calls and call volume over by hour.
Okay.
But it does change.
Yeah.
By default, that's what it is. But it can be different. We can have a histogram of any property of the calls. So this is the call level of the hierarchy. So one of the properties of this software is you can smoothly zoom in and zoom out to get the different levels of the hierarchy. And so here, right, there's a very funky call. This call is really an outlier. It's an unhappy call that spent really the longest time in the call center for that hour. Right, we can zoom in and out very smoothly and automatically with this software to try to, so that we don't get lost in the space. Before we added that feature, by the way, it was very easy to get lost in terms of which hour you were looking at, right? The hour that you're looking at is also reflected in this dial here without the smooth zooming feature. So that's also zooming in at the individual calls. You can see that the variety of the length of times is really high. Right? Some calls are just a few seconds and some take hours. I can say that I was also on the call center phone call for 2 hours once for my iPhone. So I was, it's not in this data center, but I've been there.
Yes, sorry, I was just going to say, what does this call centre deal with?
I don't remember. This might be a Vodafone or it might be Vodafone. I know that's about. No, I don't remember.
Okay.
I don't remember. Yeah. And these are different filtering options, which I think okay. Rich is demonstrating some of the options with the histogram, so you can map the histogram to any property. For example, the volume, the amount of time spent. Usually, we're choosing some component like the amount of time spent in the IVR, or the amount of time spent on hold, or the amount of time speaking to an agent. We're usually selecting these different components or these different subsets of the phone calls and looking at them in more detail. Right, we noticed a rise in abandoned calls at around 1 o'clock p.m., which is around lunchtime. So we can apply different filtering options to the calls. And these are all different ways we can filter the calls and focus on subsets. Right. So there we zoom in. And this is like call duration, for example. We can focus on call duration, or we can focus on just the length of time spent in the IVR. But we can filter out the short calls, right, for example, or the calls with a short amount of time. This is focusing on the queue time. So we noticed a rapid increase in the queue time just before lunch and after lunch by using this focus and context options, which aren't showing up on that display so greatly. Right, so these are, we can focus on, for example, only abandoned calls. Right, that's a possibility. We can choose any part of the call and just focus on those ones with longer IVR times, shorter IVR times. Usually we're focusing on the calls with longer durations, either longer IVR, longer wait times, or longer agent times. Okay. We can click on a call and then see exactly what happened during the call, the amount of time spent in the IVR, the amount of time spent in the queue. the amount of time spent with an agent, right, and the total amount of time. So this call actually lasted over an hour, which is a long time, right? It was a so-called consult call, which actually means it was made by one of the employees inside the call center. So the call center generates a lot of its own calls. A huge number of calls are the result of the original call being placed with the wrong agent, with the wrong area of expertise. That generates another like 40% of all the calls in the call center or something like that, which means the IVR is not working, generally. So we get the overview, we have our filtering and subset selection options, and then we have our detail options. So we have the visualization mantra we tried to implement, right? And we can look at the events in different ways, right? We can look at them in different views. Any questions about the call center?
Did any chance being implemented in the call center after this study?
That is a big challenge to get the software into industry, right? It's at a certain technology readiness level, but it's not at the technology readiness level that the company needs to, use it in production, right?
So what's the future for the software like? Is it a one-off for the company or the...
It's very uncertain. Let's say, but this is the issue that comes up like every day, right? This is what the whole visualization community talks about at every conference, at every event, right? What happens to the software at the end, right? I call it actually the software development death cycle.
Well, that's a case project, so maybe
yes, you're right. It's a very industrial oriented.
I don't know. Only one that keeps things going together, which is successful software has been sort of these sounds which have been taken up by the universities themselves. I don't know. We have. I see there's call centres in most universities now with IT services, and those call centres on your clearing. The question is how easy is it to access and then get embedded into the annual clearing system of the university, and see, and then just add that as a service for each year to come find out.
It's also possible that there's a false premise in the expectation that we will convert our software into industrial use.
Yes,
It has long been my view that our most powerful form of tech transfer is by getting rid of our students. Or more accurately, by training people and then letting them go and develop things directly in the industry. It doesn't get reported, but that doesn't mean to say that it's not powerful. The problem is that it doesn't meet the current expectation that you have measurable outcomes, nor that you be able to attribute them directly to the particular research project. So there may indeed be a false premise in the assumption that extending the software and turning it over to a corporation is in fact the best way of doing a tech transfer.
Yep, definitely. If I had my way, I would love to see funding, especially for that purpose, that says if you have software that's at this technology readiness level, a research prototype, and you want to bring it up a few levels in the technology readiness scale to get it to the industry level, we have funding just for that purpose. And then as academics, that's what we like to do, right? Apply for funding.
It's called Innovate UK funding, so that's what it's there for.
It
requires a business to get linked. It requires you to have a business to. That exists. And the question is whether it's a purpose. Whether it's the purpose. That's what I'm saying. One of the ones I think Southampton was the best one of doing their data archiving system, because they used it internally on a very regular basis and became very robust. And that's why, in some sense, we don't use that opportunity so much. Looking internally and saying, what could we have on our system which would work?
Yes. But it's a topic that comes up every every time, every year, like what happens to this software.
Right.
Good?
Anyway.
Yes.
Okay,
we're
great.
done, yeah.
Okay. Well, anyway, really, I think we all need to say thank you very much indeed to Robert for the interesting talk. So. Yes, indeed.